Hello everyone. So today I, Swati Verma, Assistant Professor at Calcutta's University School of Medical and Allied Sciences, Department of Pharmacy, shall be discussing with you about IR spectroscopy. So IR spectroscopy is currently most widely used spectroscopic techniques if we perform the qualitative as well as quantitative analysis of any compound. First, the thing that we should know is that the full form of IR. IR is your infrared spectroscopy. Now, the most important thing is why to use IR spectroscopy. Like every spectroscopic technique has a purpose for which it is used. IR spectroscopy is used for the determination of functional groups present in a particular compound. So each and every compound has a number of functional groups present in it. So for the determination of functional groups, we can use IR spectroscopy. Further, the type of the carbon present in that particular compound, like that particular carbon is sp hybridized, sp2 hybridized, sp3 hybridized. This can also be determined by using IR spectroscopy. Moving forward, first we will discuss about the introduction to IR spectroscopy. So it is a type of a spectroscopic technique in which the interaction of electromagnetic radiation in this case is your IR radiation, occurs with the matter. So we are having a particular matter. This particular matter will interact with your incoming IR radiation. And after interaction, what will happen? Your molecules which are present in your ground vibrational state will show a transition from its excited vibrational state represented as V1, and here the molecules are present in your ground vibrational state. So these particular molecules will absorb the energy of incoming IR radiation and will show transition from your ground vibrational state to your excited vibrational state. So whenever IR radiation interacts with the matter, there occurs the absorption of radiation. That's why it is known as absorption spectroscopy. So IR radiation, like that of UV visible spectroscopy, is also a type of absorption spectroscopy. IR spectroscopy is used for the determination of functional groups like OH, NH2, C double bond O, ester, ether, NO2, aromatic, aliphatic, sp, sp2, sp3 hybridized carbon. So each and every type of functional group we can determine by using IR spectroscopy. Infrared radiation is an electromagnetic radiation in the wavelength range which is adjacent to and of less energy than your visible radiation. So it just lies after your UV visible radiation. The infrared region starts at a wavelength of about 0.7 micrometer and ends at a wavelength of about 500 micrometer. So the starting range of your IR region is 0.7 micrometer and it ends at your 500 micrometer. Why to use IR? So it is used to analyze the functional groups. The frequency of radiation is often expressed as a wave number rather than a wavelength of frequency. So in case of IR radiation, we express the frequency of radiation in terms of wavelength, wave number rather than wavelength of frequency. And we all know that the wave number is directly proportional to energy. So higher the wave number of a particular radiation, higher will be its energy. Wave number is the inverse of wavelength, so we can represent it as nu bar is equals to 1 upon lambda h nu upon c, where nu bar represents your wave number, lambda is your wavelength. We can also represent it as Planck's constant to frequency divided by c, which is your speed of light. So your higher wave number corresponds to higher energy. Now, the IR region extends from 0.8 to 1000 micrometer. Further, this particular region can extend up to 0.8 to 1000 micrometer. The region of 2 to 15 micrometer is generally used for analysis. This particular region of 2 to 15 micrometer is known as your mid-IR region, and we use this particular region for the purpose of analysis. The band positions in the IR spectrum are represented here as wave number, whose unit is centimeter inverse. As it is inversely proportional to wavelength, IR region refers to that part of electromagnetic radiation which lies between the visible and microwave region. So IR region lies between your visible and microwave region, the ending of visible region and the starting of microwave region. Very simple compound can gives you IR spectrum. We can use IR for the determination of functional group, and each compound can contain a number of functional groups. So the spectra that is generated after the analysis is quite complex. We can get each and every peak of a particular group present in that particular compound, but that particular complexity, as it is having each and every peak, so the chemists usually use that particular complexity as an advantage when matching the spectrum of an unknown compound with that of an authentic sample. So they can use that particular complexity of the spectrum to match with a particular compound in order to identify it. A peak-to-peak correlation is excellent evidence for identity. For this, you can go for your peak-to-peak correlation, whether this particular peak is present in this compound or not, this particular peak is present in this compound or not. So you can go for your peak-to-peak correlation. Next, the IR region is further divided into three particular regions. First, the region that we are having is your near IR. So near IR region starts from 0.8 and it ends at your 2.5 micrometers. So the range of your near IR region is from 0.8 to 2.5, and it is mainly used for the determination of hydrocarbons. Next, we have mid IR region. Mid IR region is known as your functional IR region, and the majority of peaks are present in this particular region only, and this particular region has a wavelength range of 2.5 to 15 micrometer. After that, we have far IR region. Far IR region has a range from 15 to 1000 micrometer, and basically rotational changes occur in this particular region. So first region is your near IR, then we have mid IR, after that we have far IR. Near IR 0.8 to 2.5, mid IR 2.5 to 15, and far IR from 15 to 1000 micrometer. The fundamental region from 2 to 15 micrometer is the region that provides the greatest information for the elucidation of molecular structure, and most IR spectrophotometers are limited to the measurement in this particular region only. Absorption of IR radiation will cause changes in the vibrational energy in the molecule at your ground level. So basically what is happening in case of UV, we are talking about the electronic changes, whereas in case of IR, what will happen, our vibrational changes occur, like the molecule is, we talk about that the molecule is present in your ground vibrational state, and whenever your IR radiation comes, it will show transition from your ground vibrational state to excited vibrational state. The energy state is not changing, it's just the vibrational level is changing. Ground vibrational level set to your upper, that is excited vibrational level. So for energy to be transferred from the light source to the molecule, the frequency of vibration of each must coincide, and moreover must be accompanied by a change in the dipole moment of the molecule. This particular change in the dipole moment is the basic necessity for a molecule to be IR active. If a molecule is having a dipole and they are occurring a change in the dipole, so that particular change in the dipole will generate an electric field around itself. Whenever a particular molecule is vibrating, what is happening? That particular molecule can be a IR active or IR inactive. See, if we are having a particular molecule like HCl, so HCl is having an electronegativity difference, so the molecule should have electronegativity difference so that we can get a value for charge. We all know that the formula to determine your dipole moment is equals to your mu is equals to delta into d, where mu is your dipole moment, delta is your charge, and d is your distance. So whenever a molecule is having a electronegativity difference, it will develop a particular charge, so we get a particular value of dipole. Now suppose that particular molecule vibrate in the sense we can assume it like we are having a spring and that particular spring is attached to your two balls. So what will happen whenever you stretch or bend this particular string, the particular bond length or bond angle will get changed. So due to that, this particular distance get changes. If we are stretching a particular molecule, what will happen? The distance get increases. If we are bending a particular molecule, the angle will get changed. So in both the cases we experience a change in the dipole moment. Now whenever this particular change in dipole moment occurs, what will happen? This particular change in the dipole moment will generate an electric field around itself, and that particular electric field is having certain frequency. Now if this particular frequency of your molecule matches with your incoming IR radiation, the incoming IR radiation will also have a certain frequency. So if both the frequency match, your molecule will absorb your incoming IR radiation and will show transition from your ground vibrational level to your upper vibrational level. So a change in the dipole moment is must. Just as your UV visible absorption spectra are strictly caused by changes in the electronic, vibrational and rotational energy, so IR absorption spectra are due to changes in the vibrational energy accompanied by changes in the rotational energy. So only vibrations that result in a rhythmical change in a dipole moment of the molecule are observed in the IR. So that particular vibration in which the change in the dipole moment is occurring are only appeared in the IR spectra. Each and every vibration is not present in the IR spectrum. The use of IR spectroscopy was begun by Wilbur K. in 1950s, and as a result, IR spectroscopy became an accepted technique. So first it was started by Wilbur K. in 1950s. A criteria for IR absorption is that there should be a net change in the dipole movement in a molecule as it vibrates or rotates. So here you can see a particular vibration in a diatomic molecule. So first a molecule should be diatomic. There should be a electronegativity difference in that particular molecule. Monoatomic or diatomic homonuclear gases like your H2, O2, these are all IR inactive. So if we are having this particular molecule who is having an electronegativity difference, this particular molecule when vibrates, there occurs a change in the dipole moment. Infrared absorption generally corresponds to changes in vibrational and rotational levels in a molecule, that is the changes in the direction of vibration of a portion of molecule in relation to the remainder molecule or of the rotation of the molecule about the center of gravity. So whenever a molecule vibrates, there occurs a changes in the vibrational and rotational level. As our total energy is equals to your E electronic, vibrational and rotational, IR radiation being less energetic, these cannot produce a change in the electronic energy, but they are sufficiently energetic to produce a change in the vibrational and rotational energy levels. In most cases, changes in the vibrational level require more energy than changes in the rotational level. Infrared absorption occurs when the frequency of the alternating electric field, which is associated with the incident radiation, matches a possible change in a vibrational or rotational frequency of the absorbing molecule. So whenever the frequency match, there will be absorption of radiation. So when a match occurs, electromagnetic radiation can be absorbed by the molecule, which cause a change in the amplitude of vibration or a change in the rate of rotation. In order for the electromagnetic radiation to be absorbed by a molecule, it is necessary for the molecule to undergo a change in the dipole moment. If no change in the distribution of charge in the molecule occurs, the varying charge in the electric component of the radiation has nothing to interact with the molecule. Molecule that has a completely symmetrical charge distribution and in which no change in the dipole moment occurs when the molecule vibrates with a different amplitude or rotates at a different rate do not absorb your IR radiation. Now we are having certain substances which are IR transparent, like substances that are transparent to IR radiation are primarily monoatomic, and your homonuclear diatomic gases like your helium, neon, chlorine, nitrogen and oxygen. Why some frequencies to be absorbed? Energies in the IR radiation corresponds to the energies which are involved in bond vibration. Fundamental vibration is your E total is equals to E electronic, vibrational, rotational and translational. IR absorption involves change in vibrational energy and rotational energy. Your polyatomic molecules are having 3 degrees of freedom. Mode of rotation is 3 rotational degrees of freedom, non-linear, and 2 rotational degrees of freedom, that is linear. Your mode of vibration is usually, your number of normal modes are 3 and 6 in case of non-linear molecules and 3 and 5 in case of linear molecules, where n represents to your number of atoms. This was all about the introduction to IR spectroscopy. Now for further details you can refer to these particular references. These are the names of certain books which you can refer. And at last, thank you.